Hello, childrens. So by now, these rules are becoming quite, hopefully, drummed into your head. If you get these right, and if this basic understanding is really firm in your brain, so check through them. Are they really clear? Are you okay with all of those? Because then learning the rest of chemistry becomes much easier if you just learn these rules as we go along. Same as you learnt to read. You learnt to read because you knew what the letters said and you knew what sounds they made. If you know the basics of chemistry, the rest of it becomes really straightforward because you have a firm foundation. Now, I'm going to change to a pen so I don't make a mistake. Right, so what have we done so far in structures and bonding? Well, we've said that some atoms need to give away an electron. There's a little negative charge, an electron. And other atoms like to gain them. This first atom then becomes a positive charge, and that one became a negative. And they do ionic bonding. The ones that give them away are metals, and the ones that take electrons are non-metals. And that was our first type of bonding. Number one, ionic bonding between metals and non-metals. Then we moved on to the fact that what if you have a non-metal and a non-metal and they both want to gain? And we did this idea that, they can do sharing, and we call that covalent bonding. And it forms simple molecules like O2, H2O, liquids or gases. And then we went a bit further, saying that some non-metals, and the one we studied in detail is carbon, some non-metals actually do giant covalent bonding. Covalent. Sorry, I had to phonetically spell it. So, giant covalent bonding. And there was different forms of carbon. When it had 4 bonds, it was diamond, and when it had 3 bonds, it was graphite, and then even different forms of graphite when we looked at graphene and Buckminster fullerenes. And now we're on to the last type. So it should be quite easy to work out what it is. We've done a metal and a non-metal. We've done a non and a non. And now we just need to do with, well, how do metals bond either with themselves or with other metals? And that's the last type of bonding. And it's given the best name out of all of the bondings. It's metal bonding, so they called it metallic bonding. It's the most straightforward. It's probably the easiest to understand. But let's move on. And we'll see if you think the same. So good and so easy, they actually named a band after it. And not my favourite by any means, but I would suggest a listen to Enter Sandman. Very classic. Okay, I would suggest write out the questions, fill in the answers. You've got your title, metallic bonding. We'll go through the answers in about 2 minutes. So you pause for 2 minutes and then we'll get on. And welcome back. Why can graphite conduct electricity? And we said in graphite there was 3 bonds, but there was 3 electrons. Some of the electrons, like in metals, they're free to flow around, and we'll know more about that by the end of today's lesson. What do atoms become when they lose or gain electrons? If you lose it, you become a positive, and if you gain it, you become a negative, and those are ions. So atoms become ions when they lose or gain electrons. Diamonds are an example of a giant covalent substance. And it says here, define the term which describes a substance which is made of only one type of atom. It's only one type of atom. That's easy. That is an element. Doesn't matter if you have 1 iron atom or you have 1 billion iron atoms. It's an element. It's just made of that one type, iron atoms. And the same for the other chemicals on the periodic table, the other elements. Okay, hopefully you've got most of those right, and if not, you understand where you went wrong. Right, on to metallic bonding. So, what's the problem? And that's where we always start with the bonding. It all goes back to rule 9. Rule 9 on that very first slide. What do they all want? They want full shells. And that's all of structures and bonding, all about atoms getting full shells. And this is a typical metal. I've put here 1, 2, 3, easy as. Now, obviously that's the start of a Jackson song, but that's for you to discover, not me to influence your music taste. What's the problem? Well, it's got 3. This one I'm drawing on, it's got 3 on its outside shell. Metals lose 1, 2 or 3 electrons, and in this case aluminium wants to lose 3 to get a full outer shell, and then it will have that ring there of 8, so it'll be full. So all around it there's other ones, they all want to lose 3. Oh no, I want to lose 3, I want to lose 3. So they play a trick, and this one says you have it, you have it, and you have it. But at the same time this one's saying you have it, you have it, you have it. And this one goes, no, you have it, you have it, you have it. But then this one's got this one, then it says you have it, and then it says you have it, and then where does that electron actually go? So I'm going to change colour pen. Here is an electron, and I should draw it as a cross really, there you go. And let's follow the path of it. And that electron is just being passed around all over the place. They don't want it. They're all sharing it in a way, but it's just being passed back and forth all over the place randomly. But so are all those other outside of shell electrons. Let's follow another one, just because it's good fun. Let's follow this one here. You have it, 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 you have it. Look at it, you have it, you have it. Poor electron must be really confused, but actually it doesn't have feelings because it's only an electron. Well, I don't know it has feelings, but I don't think it does. Anyway, right, what a neat diagram so far. Some of you I know would love to write that in your books because that would make your work look so neat, or not. So the point is, they all throw all of their electrons at the other ones, and what does that leave them like? Well, it leaves them looking like this. So here are those electrons that they're throwing around between them, and here are them, their original, and now they've got a full outer shell. So it's nice and happy with its full outer shell here, but it's got rid of some electrons, so it's left with a, see if I can get a white on there, it's left with a positive charge in the center. And again, this isn't the diagram I want you to draw. This would be a silly diagram. Far too many little things to draw. That's better. Now, how do we explain this? Well, we know that metals are really strong, and we know that they're flexible and bendy and stuff like that. So what have we actually got here? We've got, because remember, if they've all lost electrons, so metal atoms, let's write it. Metal atoms lose electrons and become positive ions. Now, what we call these electrons, like this purple one here, oh, I'm outlining it at the moment in white, but let's outline it in red. This one here, this is an example of an electron that's no longer in a shell. We call those, there's 2 words. Now, the word I usually use to introduce it is we say that those electrons are free from the atoms. There's a better word for it, and it's the word that is in the spec and also you're expected to know. They are delocalized electrons. So there are free delocalized electrons. So that describes what's happening. Here is an atom, like the ones we were saying, that loses the electrons on the outside shell and becomes positive. And here are some delocalized electrons that are just floating around. Right. How does that make metals solids and strong? Electrostatic forces between between the positive ions and the free C of electrons. It's almost a little bit like English. This free C, why is it called a C? Because they just flow all around the place, just like water in the sea. So they're flowing and going, and I'm making the diagram messy again. So let's get rid of my messy from the diagram. There we go, and we'll get rid of that. That's the diagram that you need to pause, and then if you add some labels, what it's probably worth doing is explaining that metals are solids and they have high melting points because the positive metal ions, and we've got this written down here at the side, the positive metal ions there and the free C of electrons have strong electrostatic forces or electrostatic bonds, attractions between them. And that really sums up metallic bonding. So there's your diagram, there's your notes. Exactly the same. Positive metal ions sharing a free sea of electrons. And those electrons aren't stationary, they're moving all over the place. Because when we come on to later on, this explains why do metals conduct electricity. They conduct electricity because electrons can flow through. If we gave them all a direction so they weren't moving randomly, if they were all moving this way, we'd have a flow of electrons. And you'll meet that more when you come into physics and we're looking at a flow of electrons, because that's what electricity is. That's how you're able to listen to this now and power your computer. Right, this is here for a reason. It's another explanation. Just check yours and check this one. Pause for a minute. Is there anything on here that isn't clear in your notes? And then continue. Right. Pause, draw, think, look at the periodic table if you need to. See if you get the type of bonding right for these. And when you're ready, did you get them right? And if you didn't, can you work out why? So where you've got ionic, it's a metal and a non-metal. Where you've got covalent, it's non and non. And where you've got metallic, it's just metals. And then 4 properties for this metallic bonding. So we've got the structure now, this metallic structure. What about the structure? Well, metals, there's a thermometer here and a symbol. Metals conduct heat. Those electrons can quickly carry energy through the metal and make it vibrate quicker, the particles, which is what heat is. And you'll know that from when you've done about particle theory and particles vibrating when they get hotter. Metals are malleable. The way I remember it is if you hit them with a mallet, they're not brittle, they bend. So look at this bent spoon. They're malleable. Those positive ions can slide over each other. Metals conduct electricity. They conduct electricity because the electrons can flow through. They have a free sea of electrons. So you've got a reason for each one of these when you record it. And the last property here, they have a high melting point. So we can use them for saucepans and all sorts of things where heat is. Why do they have a high melting point, most metals? Well, they have a high melting point because there are strong electrostatic attractions between those positive metal ions and the free sea of electrons, just like you've just described. Right, some questions to answer and mark, and then the last bit. Now, when I said a minute ago that metals were malleable, why are pure metals so easy to bend? And it's because this row here can slide over the top of this row, and metals are easy to bend when they are pure metals. And pure means Here is a pure piece of iron, Fe. Every single one of those is Fe. It's just Fe, just iron. Pure, quite easy to bend. Here, however, we've mixed in the purple ones. So here's my Fe, and here, for example, I've mixed in some chromium. By mixing the two different metals, look what I've done. I haven't got neat lines now going across, so therefore it changes the properties. That is called an alloy. An alloy is any mixture of metals. We'll do a bit more about that in a minute, but those aren't bad diagrams to have before you move on. And our best known alloy that you'd use every day, because you probably got a lift to school or your parents outside your house have got a steel, mostly steel car, and most parts on your bike will be steel, and most support beams in buildings will be steel, and the legs on your chairs and tables at school will be steel. So here we've got this pure metal that's quite bendy. So number one, the pure metal can be bendy, and here, number three over here, we've got this alloy. And what we've done is we've mixed those red particles, another chemical in with it. It disrupts it, it makes it a lot stronger. So iron is pure iron, which is Fe, atoms, nothing else. What is steel? Steel is usually 99% iron, 1%, for example, carbon. And you can have low carbon steels and high carbon steels. What else can we do with steel? Well, you're eating at home, and when you're eating, hopefully there isn't rust on your knives and forks. So we've made a substance called stainless steel that doesn't rust anywhere near as easy as iron. So stainless steel, for example, can be 80% Fe, 1% carbon, and 19% chromium or nickel. So chromium is a very shiny metal. Iron is quite a cheap metal. Mix the two together and all of a sudden we've got this type of steel that doesn't rust and stays really shiny. So it looks good. It's not a dark grey like iron or steel is. Stainless steel would look nice and shiny, etc. And you can get different qualities. So for expensive knives and forks, it'll have more chromium in it, and for really cheap ones, it will have a tiny amount of chromium. So steel is stronger than the pure iron. And that's it for today. So there's many other alloys to look at. There's many other alloys to look at in the future. But for now, the focus of this bit is metallic bonding and the metallic bonding properties, and just an idea of what alloys are. Okay, thank you for listening, and hopefully you understood that, and your notes will look good when you send them in to your teacher. Thank you very much.